Welcome. In this video, we're going to create our very own AI video generator that's going to be based on the Animate Diffusion paper. And we're going to look at the code to train our very own model and then use it to generate our very own original AI videos. And we're going to go through the code and the steps to get that done. So what we're going to be doing specifically is training a motion LoRa on top of an Animate Diffusion unit. So to get started, let's take a look at what a diffusion system is. A diffusion system basically is trained to receive a noised image, a noised version of data, and then to output a slightly denoised version. And over time, if it's done iteratively, it can generate some very original content. A diffusion system has three main components: a scheduler, a unit or any model that does the denoising, and obviously a data loader. And we're going to be implementing each one of these three ourselves. The scheduler is going to be doing two different tasks. When it's training, it's going to be noising the images so that the model can guess to separate the noise from the data itself. And during inference, when we're generating new videos, it's going to be denoising noised videos. So basically, it's going to take pure noise at first and progressively, with the help of the model, denoise it until it creates an original video. And the diffusion systems have really shown to be extremely performant in generating original and honestly impressive content. So basically, the scheduler that we're going to be using, we're not going to implement a scheduler from scratch. To keep things simple, we're going to just take one off of Hugging Face and use it within our system. We're going to focus a little bit more on the unit, the model itself. The Animate Diffusion paper actually takes the Stable Diffusion unit and adds an adapter on top. So basically, instead of generating images, it generates short videos. The Stable Diffusion unit actually receives data that's in the shape of batch size times channels times height times width. And with the Animate Diffusion adapter, this progressively changes to batch size times channels times frames. So the concept of time is added times height times width. And the motion LoRa, what it does, it basically adds a small LoRa on top of the Animate Diffusion adapter. So the model's input outputs don't change, but it's easier to train that way. And then you still get the batch size times channel times frames, height, width, input and output. And that we're going to plug it into our diffusion trainer, and we're going to do all of this in code to really see how it happens. The advantages of this approach are it leverages really everything that's been done in image generation, all the pre-training that's been done to generate small moving videos. And this is obviously much easier on the VRAM as well as other approaches which train from scratch and which don't necessarily go based off of an image generator, but really are dedicated video generating AI models. And there's pros and cons to each, but one big pro to this I find is really that it's much more approachable on consumer hardware. So with that said, let's get started and let's delve into the code. So let's take a look at the code. First of all, we're going to import from diffusers the Animate Diffusion pipeline. And with this, we're going to get the model, the scheduler as well, and the adapter as well. So basically, this is the code from Hugging Face. You instantiate the motion adapter, you get it from pre-trained, the model ID, the pipeline, and the scheduler is a DDIM scheduler that you also call from pre-trained from the same repo. And now the initial pipeline is all set up with all the components of a diffusion system, but obviously this is not going to train anything for us and we'll have to write our own training code. So once you have the pipeline loaded, you can actually inspect the unit, and what you have is a unit motion model. This is a subclass of the UNet 3D conditional model. And you can basically take a look at the entire UNet and all the different layers. What this is, since this is a conditional model, it's going to expect basically a video type data. So basically, it's going to be batch size, channels, frames, the different frames, height and width. But it's also going to need embeddings of uh, a prompt. So a prompt that's been embedded into a prompt embedding that basically describes the video. So that'll be the condition that it's going to take. And it's also going to need a time step as all diffusion units do. One thing that's important here now, since we're not going to be training this model directly, but rather we're going to be training a motion LoRa on top of it. In order to create our LoRa, we're going to have to look at the attention module. And LoRa's are typically meant to be attached to the linear layers within the attention module. So here the layers are 2Q, 2K, and 2V. Now it's important to take these three in note for our next step. And you can just go ahead and send the pipeline to CUDA, make sure everything fits. Here, I think it's usually always a good idea to make sure you have your shapes right, because when you're going to be creating the data loader next, it's going to be important that everything is correct. So I have actually, sometimes you put the frames before the channels and then nothing's working anymore. So just make sure that the shapes are right. So we really have the batch size, channels, frames, height, width. And this is the time step. I just put in something random, and the prompt embedding. You send it in to the pipelines unit and you get an output, and the output shape is the same as the noise or the supposed noise that you've inputted. So this is functional. We can move on to the next step, and we can see this is basically just looking at the unit again. Then, in order to create our motion LoRa, we call from PEFT our LoRa config and get PEFT model. PEFT is parameter efficient fine tuning. So this is basically a quick and easy way to obtain LoRa's or create your own LoRa's. In the config, we're going to put the target modules are going to be the linear layers within the self-attention module. So 2Q, 2K, 2V. These three layers, as we mentioned, it's important to point them out. And then you can call get PEFT model with the model that you want to attach a LoRa to and your LoRa config. And then you have your model. This is the PEFT model. And this is basically the UNet motion model with a LoRa on top of it. And you can see that this is functional. And now if you call, I basically did the same thing. So the same noise, the same time step, and the same noise embedding of a prompt. You send it into the model and you get the output. Well, this is still functional and you get the output as expected of the same shape. So basically this is as easy as that. We've turned the motion model into we've attached a motion LoRa to that motion model, and now we can basically use it as a whole into a diffusion trainer. And next video, we're gonna hard code our diffusion trainer, and after that we're gonna hard code our data loader and let the training run. So follow along. If you like this, leave a like and a comment. So by next week, I'll have the video out for the code behind the trainer and the explanation about that. So how the trainer is set up and the data loader as well. So check back within the next week for the conclusion and finally how the videos are going to turn out.